So the first part of chapter 3 is really more about light than it is about optics. And so hopefully, again, from Gen Chem or physics, you remember some of this stuff, right? Light is electromagnetic waves. And so the sort of the structure of light is that we have these perpendicular waves that are superimposed onto one another. The E field, the electric field, and the B field, the magnetic field. And the reason why light is so good at interacting with matter is because lots of our subatomic particles have both electronic and magnetic properties, right? Electrons that have charge will interact with an electronic field. And because those electrons are spinning balls of charge, they will also interact with a magnetic field. Same goes for neutrons, right? Neutrons have a charge. Neutrons have some magnetic field due to spin. Did I say neutrons? They don't have a charge. Protons, sorry, nucleus. Protons have charge. They will interact with light. Neutrons, hard to detect neutrons. Neutrons were the last subatomic particle, well, the last of the three big subatomic particles to be discovered, and it was discovered less than 100 years ago. It was in the 1930s that the neutron was discovered. And so, you know, just generally speaking, very good at interacting with matter because of both the properties of light and the properties of matter, right? And then this is an image from our text here, right? The different, we call this electromagnetic radiation, EMR, right? Sometimes this is called the electromagnetic spectrum. And so we have different types of instruments that deal with a huge variety of these regions, right? And so we know that we have instruments for visible light, UV-Vis. We have instruments for infrared in IR. I talked last time about microwaves and doing microwave spectroscopy and how that's rotational transitions rather than either vibrational or electronic transitions. When we do X-ray fluorescence, there's a lot of electron microscopy that has some X-ray built in. With X-ray spectroscopy, usually what we're doing is not just exciting an electron, but removing it completely, right? It's enough energy that actually strips an electron off of that particular atom. What that does is it tells us a little bit about it gives us a actual profile of what that atom is, because if you know that you put in 300 eV of energy, and if you get out an electron that still has 200 eV of kinetic energy, you know that 100 eV went into pulling it off that atom, right? And there are only certain atoms that have ionization energies of 100 eV. eV is electron volts. It's not a unit we use commonly in chemistry. That's a physicsy unit. We're used to joules, right? Electron volts are much bigger than joules, and so we can talk about an electron volt more easily than we can talk about joules. Right? Gamma rays, we really don't use that often in chemical analysis, nor do we use, you know, TV and radio waves. There are terahertz microscopies. So tera is the prefix for 10 to the 12. And so that's sort of in between TV and microwave here. Microwave is you know, somewhere really in here-ish. And so terahertz is sort of tops out at 10 to the 12, and so it's in there somewhere. And terahertz spectroscopy is for some really low frequency vibrations. We think about this for sort of huge molecules that just move very slightly. this is kind of a new field. When I was in graduate school, 2008 to 2013, there were sort of lots of buzz about terahertz spectroscopy. And so it's a relatively new field, the last 20 years, 25 years. I do not plan to go sort of into the details of E equals H nu and E equals HC over lambda, C equals lambda nu, right? If you need refreshers on this, our textbook talks a little bit about it. Pick up a Gen Chem textbook or a physics textbook if you need more. Of course, you will always have the constants. I'll give you C, I'll give you H if you need them. Well, no, I won't. They'll be on your equation card. Put the constants on there if you need them. Just a small point about that. I generally will give you an equation if you need it for a point penalty, right? I will always give you constants if you need them for no penalty. Okay. All right. So that's talking about electromagnetic waves, talking about light. Wave mechanics, again, I just wanted to briefly go over some of the ways we think about light. We can have a multi-wavelength source, right? We call that a broadband source. Because it emits a variety of wavelengths. And so here they're talking about sunlight as a broadband source. And you can see as we move down that list there, we move from having lots of different wavelengths to having a single wavelength. In B, these are out of phase, right? When we talk about phasing, we're talking about our amplitudes, our peaks and our valleys lining up, right? And so these are not in phase, and so these are non-coherent. And then an example of that is an LED, something with a single light source. It could also be, just a tungsten bulb with a filter after it. If you work in the theater, you know that you put in some plastic gels between the light and the stage so that you get one color of light that goes down there. And so you get a single light source, a single light, but it's not in phase. Once we put things in phase, that's going to be more powerful, right? If we can line up all those waves, then we're going to get some constructive interference. And so we're going to have a more powerful beam. And so that's when we move to lasers, right? These are in phase, and we call that coherent light sources. Lasers are also, because they are coherent, they tend to also be collimated. We're not going to talk too much about that in this class. But a collimated light source means that all of the beams are oriented in the same direction. And so a collimated beam would look like this, right? Whereas uncollimated beam or a diffuse beam would look like that, right? If you've ever played with a laser pointer, you know this is true, right? There's a very small dot that you get rather than with your LED flashlight on your phone that lights up a big old area, right? These are the two different ways of thinking about it.
So, Dr. Davis, are you saying that when the waves are not in phase, then they're going to be uncollimated?
They're really different phenomena. It's just I'm just adding here that lasers are usually, not always, but usually collimated.
Okay.
And that most other light sources are uncollimated. The physical design, the engineering of a laser that gets it to be coherent also gets it to be collimated. And that's lots of engineering to do to a non-coherent light source to get it to be collimated.
Okay.
We can do it. It's just we don't often. And then again, with wave mechanics and talking about sort of how waves interact with one another, if we have our coherent beams, right, where our peaks and valleys line up, then we're going to get that constructive interference. And when they don't line up, of course, we're going to get destructive interference. The thing about constructive and destructive interference is that in order for it to look as clean as this, right, they have to be exactly the same wavelength, and they have to be either exactly additive or exactly destructive, right? And this is a kind of a rare occurrence, especially when we're talking about, you know, if we're talking about normal light sources, we don't have just 2 photons traveling. We've got 2 trillion photons coming out of it every second, right? And so it's going to be rare for us to have a situation where we have sort of totally destructive interference or totally constructive, either way. Our textbook gives examples of the single slit and the double slit experiments, right? I'm hoping that you've talked about these in a physics class somewhere along the line. And so I'm not going to go into it too much. It's good to know about diffraction and things like that. But from my point of view, it doesn't play a huge role in what we're going to talk about in this class. So reflection versus refraction. And when we talk about this, we usually talk about mirrors versus lenses. Again, this is probably something that you talked about in physics, but we're going to use these terms a lot, especially in the first part of this class. And so I want to make sure that we're all on the same page. When we talk about incoming light, we're always going to talk about it being incident, or the incident light, the incoming light. Those are interchangeable words. And so the light coming in is always our incident ray. And then if we have a flat mirror, right, that's the assumption here, that our mirror is perfectly flat, then I is equal to R. The angle of incidence is equal to the angle of reflection. And those are measured, obviously, from the normal, which is 90 degrees from our mirror surface. Refraction, on the other hand, is caused, what's it caused by? Anybody? Anybody? Differences in?
Like how the wave travels through the material or something.
Yeah, yeah, we have a name for it. It even sounds kind of like this.
The diffraction?
No, we'll get to diffraction. It's called the refractive index. Have you heard this term? The refractive index?
I heard it on the MCAT, but still never understood it.
Fair enough. And so that refractive index essentially tells us something about how different the wave travels in one material versus another, usually versus vacuum. That's what we think about as being sort of our pure material. The thing about refractance, or refraction versus reflectance, is if we look at the line, if we look at the line of our light, right, it does not stay in the, it does not stay in the direction it was going. it shifts direction, right? Well, I shouldn't say that. The direction is actually exactly the same. It just shifts position, right? And so in refraction, in and out of your prism, you're going to have sort of exactly the same angle, but it's going to be shifted in space. This is the reason why when you put your cuvette in a UV vis, that cuvette holder is really tight, right? That cuvette holder is really tight because you don't want that cuvette to shift. You don't want that cuvette to wiggle around, because then that light beam is not going to be going directly through the center of that cuvette, and it may not make it to the detector. There's an image in our text where the cuvette is a little lopsided, and it's enough to make the light beam miss the detector. I mean, in modern instrumentation, you'd have to be so lopsided for that to really happen. But that's one of the reasons why the cuvette holders hold on to a cuvette so tightly, and so they can make sure that it stays in that geometry. The refractive index, since we're here, is given the symbol N. It's kind of a scripty N usually. And that's C over V. Right? C is the speed of light. That's a constant. V is the velocity of light in that material. Right? So the speed of light in the material. And of course, C is in vacuum. Right? And so when we talk about the speed of light in air versus the speed of light in a vacuum, they're really close. The refractive index of air is 1.003. Right? They're really close together. But when we move up to something like water, water has a refractive index of 1.3. Right? And so it's 1,000 times more different than air is. And so we have to take that into account. Usually we don't really take into account air unless we're doing something sort of super high precision. Okay. What does that look like? That looks something like this, right? If we have our two materials, air and acrylic in this case, as long as that surface, that interface is a pretty smooth interface, we will get both of these processes occurring, right? We have our incident light coming in, it hits that surface, and some reflected light gets bounced back. The rest of it moves through, right? We don't often think of light as matter, right? Because even though photons have a rest mass, but photons never rest, it's a real quantum physicsy thing that I don't want to think about. But thinking about light as having inertia, having momentum, is something that we sometimes do. Light would much rather continue on the path that it's going than be turned. And so the amount of light that's reflected is actually relatively small, as long as those differences in refractive index are not too great, right? The refractive index of a mirror is enormous, right? Because light doesn't travel through a mirror very well. And so that's why most of it gets reflected. In the situation, to determine how much is reflected, big R, we're going to take the absolute value of this ratio of N1 minus N2 on top and N1 plus N2 on the bottom. We're going to square it. Right? This is called the reflectivity. And of course, material 1 is where the light comes from. Material 2 is where the light is going. Right? As just a point, a number that I keep in my head for glass, for air and glass, R is about 4%. Right, so 0.04. And so, do you lose a whole lot of light? Well, no, but it's not negligible either, right? And so, we need to think about that when we make instrumentation, when we think through instrumental design. It's also one of the big reasons why we take a blank and why we should use whatever cuvette we're going to use and whatever solvent we're going to use when we take our blank, because depending on what that solvent's index of refraction is, depending on what the cuvette's index of refraction is, we could be losing a lot more light, right? You should never take a blank with just an empty instrument. So let's do a quick example together. Not really together. You do it together. I'm going to sit here and watch you. Feel free to talk to each other. I mean, I know Annabelle and Ashley will, but the rest of you can talk to each other. I'm reading the daily announcements. I'll entertain you while you do this work. And it has a conversion from Celsius to Fahrenheit in the daily announcement. That makes me giggle. 37 degrees. I'm frozen.
So, a question.
Ask away.
Yeah. So when the light passes through the first time, it
Yeah.
has to pass through the quartz cuvette first. But the initial N for that scenario is air or
Oh, so I'm fine with you if you want to keep it at 1. If you want to put 1.003, I'm okay with either of those. Yeah.
okay.
Yeah, sorry. Air. I'm cool with that.
I might be thinking too much into this, but don't we have like air to the quartz and then quartz to the solution and then solution to the quartz and then quartz?
For sure, yeah. So
Or back to the air?
our zoomed in cuvette, right? We have air, we have our quartz, and we've got water in the middle here. Right?
Yeah.
And so if our incident light's this way, we're going to have a reflection there, reflection there, reflection there, and reflection there, right?
Right.
Now, it doesn't matter, the order doesn't matter in the sense that if I'm doing air to quartz and quartz to air, because it's absolute valued and squared, who cares, right? Just take your number and double it. Quartz to water, water to quartz, doesn't matter, take your number and double it, right?
Right.
And so who got a number for air to quartz? It's less than air to glass.
Yeah, I will be the first to go, since if I'm wrong, I'm okay with it. 0.035, because it's 1 minus 1.46
Yeah.
over 2.46 squared.
Yeah.
Oh, yeah.
Yeah, good. Me too, I agree. How about quartz and water?
Point 0.00217.
Excellent. That's what I got. All right. Now you got to think about an engineer when you talk about this total loss. Don't think like a. Oh, never mind. Don't see what I was doing. What's our total loss? Don't say 7.44. Is that what everybody wants to say?
That would be easier.
That would be easier, yeah. So here I have 100%, right? But by the time I pass that surface, do I still have 100%? Nope.
No.
I've got 96.5%. And 0.22% of 96.5 is not 0.22, right? It's a little bit less. It's real close to 0.22, but it's not.
It's 0.2123. I think.
Okay.
Do we not need to know that to continue?
Sure. It all depends on how you want to calculate it. Yes. The number I calculated was 0.9629, right?
Right.
Instead of losing 0.22, we lost 0.21. And then we lose 0.22 of that again. And we get 0.9608. And then we lose 3.5% of that. And we get out. All right. Do you follow that logic? Do you follow that process? Right? And so the loss from reflectance is 7.3%, not 7.44, because we don't. We're not always losing from 100. We're losing from whatever it is at that point. Okay. And so this is why we need UV vis that have a relatively powerful light source, right? We're losing already almost 10% of our light just from having something in the way. Not even whatever's being absorbed by our sample. And so again, this is why we need to be real sure that we actually have a blank in there when we're doing our background, because we want to account for this 7.5% loss. Right? Questions about that kind of problem? Okay. All right. The last thing to talk about is getting into this idea of narrowing down a broadband light source like a tungsten bulb, like the sun, narrowing it down so that we only have the wavelengths that we're interested in. In olden days, they used to use rotating prisms. Right? So this is a prism, just like the cover of the Dark Side of the Moon. What is that band? Somebody help.
Pink Floyd.
Pink Floyd, thank you. Just like the Pink Floyd album cover, right? You got your prism with your rainbow on one side and your white light on the other. You've got your broadband light source. Right? And over here, we get single wavelengths. Prisms are okay. They're not great. The separation that you get per prism, in order to get really fine separation, you need an enormous prism, right? And so it's more difficult to make a compact UV vis or compact monochromator when we have to use a prism. So I just said a new word, monochromator. Mono is our Greek prefix for what? One, yeah.
One.
Chroma is a Greek for
Color?
color, yeah. And ator is, I don't know, doer, machine. Monochromator. So we have a one color machine, right? This is what takes our broadband light source and gives us a single wavelength out. In most modern instrumentation, we have diffraction grating. Here's where that diffraction comes in, field. Diffraction, I think of as sort of a combination of reflection and refraction, because we're doing, with diffraction, it doesn't go through the material, it comes back out of it. Right? And so you have a single point source, and then what this first curved mirror does is it collimates that beam, right? Even though they're all different wavelengths, it makes sure they're all traveling in one direction, right? So it goes from this divergent beam here into a collimated beam when it hits the diffraction grating. And that diffraction grating will shift the different wavelengths all by a different amount. And so when we go to the next slide, I'll point that out. Last thing, this exit slit has a lot to do with the resolution or how good our monochromator is. And so the slit width is something we'll talk about in a couple of slides, but keep that in mind. I may come back to this image when we talk about that. Right. So for our diffraction grating, this is a zoomed in physicsy picture. Do you talk about diffraction gratings in physics? In sort of the normal physics? No, that's fine.
I did that.
Yeah, that's okay. So again, what happens is we have this collimated beam coming in of multiple wavelengths. It comes in at some incident angle alpha, it's going to hit this diffraction grating, and you see the way this diffraction grating works. Let me change colors here. The way this diffraction grating works is that you've got these grooves that are cut into it, right? And so these are all kind of at an angle, right? And because of whatever that angle is, and how close together those grooves are, dictates sort of the degree of diffraction and gives us our diffracted angle beta. Because those grooves are angled like this, they've made a couple of triangles here. Let me see. I don't know how many colors I have. So we have this triangle, right? And that one is made based on the point where ray 1 and ray 2 have traveled the same distance, right? That's that line right there in orange. Let me get rid of these two. That line in orange is the point at which ray 1 and ray 2 have traveled the exact same distance, right? And then this line that I'll do in red are the point where they start traveling together again, right? The blue lines that are highlighted here, this first one, d sine alpha, that's the extra distance traveled by ray 2, right? So d sine alpha is the extra distance traveled by ray 2.
I'm sorry, can you I'm a little lost. Can you clarify ray 1 and ray 2?
Sorry, these.
Oh, up there. Okay.
Sorry.
Thank you. You're good.
Okay. So the second, so think about two photons, if you'd rather think about them as particles, right? Photon 2 has to travel just this tiny bit extra before it hits the surface, right? And then when they bounce back off, photon 1, ray 1, has to travel this extra bit, right? And so d sine beta, I had a professor who did his PhD in South Africa, and he said beta all the time. Sine beta. This is the same, ditto, ditto, but for ray 1. Right? And you notice that those are not the same distance, right? But in order for us to actually get light out, ray 1 and ray 2 have to be constructively interfering, right? If they're destructively interfering, then we won't see any light. But if they're constructively interfering, then we will. Okay? And so essentially what that means is that d sine alpha and d sine beta must be integer multiples of whatever the wavelength is. So d sine beta and d sine alpha must be multiples of our wavelength. Okay. And so our equation for a diffraction grating, delta S, right? That's our difference in the path length, is equal to m times lambda is equal to d times sine alpha plus sine beta. Okay. M here is what we call the order of diffraction. We can have a zeroth order, and that's just reflection, right? There's zero difference in the path length, right? That's just reflection. For diffraction, we often use the first order diffraction, where the difference between d sine beta and d sine alpha is just one wavelength. Right? All right. How do we feel about that?
What does the red line mean again?
So the orange line is where they stop being at exactly the same point, right? The red line is where they start being at exactly the same point again. It's after they're diffracted. And so, if we took this length here, so d sine alpha is this length, right? D sine beta is this length. And the difference between those two is some wavelength, some number of wavelengths. And the number of wavelengths different gives us that order of refraction, right? So if it's one wavelength, then it's first order. If it's two wavelengths, it's second order, etc.
Gotcha.
All right. Taking a bit of a step back here, right? We have our incident angle alpha, our diffracted angle beta. The zeroth order is exactly a reflection, right? Hopefully you can see that, that the black arrows, the incoming and the outgoing, are exactly the same angle from the normal. And that first order refraction is actually what beta is showing there, right? That's the one that we use most often when we use diffraction gradients. When we talk about resolution of a grating, when we talk about resolution of a grating, so big R again, resolution, not reflectivity. When we talk about resolution, we can think about it as lambda over delta lambda. In other words, how much, what kind of separation can we get based on the wavelength? A more common way of thinking about it, where we don't actually have to do an experiment, is m times n, where m, of course, is the order, and n is the number of grooves illuminated. Right? And that's going to be dependent on the instrument rather than dependent on any kind of experiment that's going on. We'll pick up and talk about diffraction gratings a bit more on Monday, finish up optics, and then on Tuesday we're going to do a lab talking about the linear range of the EDDIS instrument. I hope your first week has been okay. I hope you have a joyous weekend. Stay safe.
Dr. Davis, do we have any homework?
If you want me to go ahead and give some homework for chapter 3, I'm happy to. Annabelle says yes. Caroline says yes. I'll put that on the Moodle.
Okay. But is that like the type of homework that we turn in on test day?
Yeah, absolutely.
Okay. Sounds good.
Okie dokie.
All right. Have a good weekend.
Go along, y'all too.
For diffraction versus the prism, do we choose diffraction because we're able to get like more orders, I guess? Like we have more control?
Um,
Like why is the prism so bad compared to diffraction?
yeah, so to get the kind of resolution, so because this resolution is the number of grooves illuminated, we have gotten to the point, engineering-wise, where we can have a diffraction grating that has hundreds of grooves per millimeter. Right? And so this resolution can be huge.
Okay.
To have a prism with the same resolution, the prism would have to be huge, right? Because there's no way to separate light further in a prism unless you got a bigger prism. And so just in terms of keeping things a manageable size and doing things sort of as efficiently as possible, diffraction gratings are preferred to prisms.
Okay, because it's easier to separate the light in a smaller area.
Yeah.
Okay. And then the more we separate the light, the better the resolution is.
Yeah, so that's what we didn't quite get to, right? That exit slit width, if that exit slit is 1 millimeter wide, but I can separate 590 and 595 by only 1 millimeter, guess what? They're both getting through, right?
Okay.
But if I
Okay.
can separate 590 and 595 by 10 millimeters, then I have better control. And if I can separate them even more, right, then we're doing it.
Okay. Cool. All right. Thank you.
Sure.